Hello everyone, this is Dr. Bugarin, and I want to thank you for watching this video. And also, it is important to mention that this video was recorded as requested by the search committee. Therefore, I would like to mention that this is the actual room where I teach either Organic 1 or Organic 2 for undergrads. And this room can accommodate up to 98 students, and my classes are always full. Okay, so also I want to mention that in a traditional lecture, I utilize a front camera to project slides or to write something here in a white paper, and also utilize the chalkboard to draw structures, schemes, equations, etc. And also almost every day during class, I have these molecular modeling, so I can utilize this to show the students the 3D, how the things will interact to produce carbon-carbon bonds or other types of bonds. Okay. So with that, let me introduce the book that we utilize for Organic Chemistry 1 and Organic Chemistry 2. Actually, this is the book, but then it's more clear that I show you here in the projection. So it's the Organic Chemistry by David Klein. And at the moment, we're utilizing the 3rd edition. And this edition covers substitution reactions in chapter 7. But at the same time, the book has eliminations. But because today we're going to talk about only substitution reactions, so I'm only going to focus on that, SN2 reactions. Okay. So what are SN2 reactions? First, let me introduce the term substitution reactions. So substitution reactions involve the exchange of one functional group from another. So as you can see in this equation, we have our starting material, we have X as substituent, and then we have a reaction, and then the product is given out a Y. So this X was replaced by Y. Okay, so that's what substitution means. We exchange one group for another. But first, before going to that, I want to show you this. Okay, this is the substrate. It's an alkyl halide. In this case, we have 2-bromobutane here. Okay, and this will be bromine will be a leaving group. But first of all, it's important to not mention that this carbon here is the carbon alpha. The carbon alpha is the carbon that is connected directly to this functional group or the leaving group. Okay, and then we have the beta, 2 beta in this case, and then gamma, and so on, until the way to many omega or all. Okay, so all the chemistry is going to happen in the alpha carbon for the substitution. Okay, so it's important the substrate to have and to identify the positions of the carbons. So this is actually a transformation, a substitution reaction where we have an electrophile in this is of substrate. And also we have a nucleophile, in this case a negative charge. The negative charge is going to go ahead and attack the carbon alpha and kick out the chloride. Now to produce this new product, which is now a thiol and the chloride. So now you can see here the chlorine was replaced by the thiol. Now we have a different compound. Okay. So what is the mechanism for this transformation? Okay. So for mechanism in this case, we have this single concerted process. Okay. So we have, let's assume that we have here or compounds. We have 2 compounds. We have a nucleophile. The nucleophile is going to do a nucleophilic attack, and at the same time, concerted is going to kick out the leaving group. So loss of a leaving group. Now we're going to have here a product. So pretty much, let me show you these models here. We have, in this case, we have the substrate, we have a nucleophile. The nucleophile is going to approach and kick out the leaving group. Okay? And why it's important to show you these mechanisms, and also they have 2 things, the nucleophile, and in this case, and the substrate. Why is that important? Because also that helps you to understand the definition and what SN2 stands for. Okay, so as you can see here, we have SN2. S stands for substitution, and nucleophilic, and 2 is bimolecular. And why this is bimolecular? Well, because it's important the concentration of the substrate and the nucleophile. Okay, what that means is that if we're going to have a reaction rate, and the reaction rate is very dependent on the concentration of the substrate. In this case, this iodo compound, and the nucleophile, in this case, sodium hydroxide. And it's SN2 reactions are second order. Okay, because the substrate is first order, nucleophile is first order, and then so 1 + 1 is 2. So this is a second order. What that means is like we double the substrate concentration, so we're gonna have a faster reaction rate. If we double the concentration of the nucleophile, it's gonna double the concentration of that. So for example, that we have substrate double concentration, nucleophile 1, it's gonna be third order, so it's gonna go a lot faster. Okay. So and for example, here we have these two reactions. Okay. And so as you can see in these two reactions, we have bromine, and the first one as a living group. We have sodium hydroxide and nucleophile, and then we have now producing alcohol. And in the second reaction, reaction B, we have bromide. Okay, reaction B, we have this bromide, and now we want to replace the bromide by that chlorine. But what I want to mention in this case is we have this bromine, which is in a primary alkyl, and this bromine is a tertiary. So they're going to go the different mechanisms. Primary is going to be SN2, SN2, and tertiary is going to undergo SN1. Okay. So here, so we have this primary, alkyl halide, secondary, and tertiary. And if we're going to think about this, if we have this substrate, and we're going to do a nucleophilic attack, as you can see, there's more space in this, so it's a lot easier to eliminate this chloride. So SN2 reactions actually are faster and are mainly occur in primary alkyl halides, or secondary also occur, but never tertiary. Tertiary is too hindered here to attack. Okay. So for that is this summary where we're going to have here the most reactive for a SN2 reaction are going to be in this case methyl, but also primary are also reactive, and tertiary are not most reactive for SN2 process. Okay. It's also important to mention that these reactions, because we're going to have backside attack, these reactions are stereospecific. Okay. What that means is, for example, that we start with this S enantiomer, we're going to now produce the R, so it's going to invert. So it's going to have an inversion of configuration. Okay. Okay. So we have that. Now we have this the S. Now we produce the type, which is an R. And so this is going to happen next because we're going to have a backside attack. Okay. As you can see here, there's possibilities that perhaps we may think that this reaction can occur where we have the backside attack, but also the frontside attack. Okay. But in these cases, you have these groups. You can either attack from the back or from this position. But you can see in this position a lot more hindered, so you're always going to prefer attack from the back. And so kick out that, and whenever you do that, then you produce this. Okay, you have this pointing this direction, now you have that. So invert the configuration. So that's why these reactions are stereospecific. And because these also reactions are concerted, so it's going to have always a transition stage going in this case. In this case, the transition stage is going to be when the nucleophile is exactly in the halfway with the living group. So all of them are the same distance far apart. So pretty much like this, right? Because you're going to have nucleophile approaching, when you are in the halfway, it's going to have a transition state. Because at that moment, your living group is going to start leaving, and then you're going to have this diagram here, energy diagram, where you have a starting material with your transition state, and now you make your product. In this case, the cyano group was replacing the bromine, okay, making more stable. So it's concerted one time, of course, concept the mechanism, and finally, just to because time is limited and we only have less than 10 minutes. So I want to show you this, and I'm showing this slide because I always ask questions to the students. And here is, for example, one question that I'm asking this: depict the expected product of this SN2 reaction utilizing R2 bromobutane plus hydroxide. And so that's pretty much it. So I normally ask the students for a lot of questions, and this is one of them. So thank you for watching the video.